Welcome folks, a calculus video on integrals involving trigonometric functions. In this video, we're going to see a few different strategies for evaluating integrals involving trigonometric functions. The two main strategies we'll see are either peeling or using the half-angle formula. Many of these strategies also involve the use of what I refer to as the mother of all trig identities, which is sine squared plus cosine squared equals 1. An equally important but slightly different version of that same identity you can obtain dividing through by cosine squared to see that tangent squared plus 1 equals secant squared. So these identities are both pretty important in evaluating these integrals involving powers of sines, cosines, secants, and tangents. Okay, let's start off with the strategy I'm going to call peeling, sines and cosines, peeling. Here's the overview. We know the derivative of sine is cosine, and the derivative of cosine is negative sine. If you have any odd power of sine or cosine, our strategy is going to be called peel a derivative. Peeling this derivative will end up motivating the u substitution we'll make in order to evaluate the integral. Okay, so here's the first one, the integral of cosine cubed x dx. Odd power of cosine, let's go ahead and peel a cosine. In other words, peel a derivative. So if I'm thinking of cosine as the derivative, that means I'm thinking of sine as a function. So that suggests modifying the squared term that's left over to rewrite that term as 1 minus sine squared. So when you stare at this, you should see a function and its derivative here suggesting the u substitution, u equals sine of x. With u equals sine of x, du is cosine of x dx, and we're left with a simple power integral 1 minus u squared du. Of course, this integrates up as u minus 1/3 u cubed, and we can go back to x world here to express the indefinite integral as sine x minus 1/3 sine cubed x plus an arbitrary constant. Okay, this same strategy works when we have other more complicated integrands too. So here's an example, cosine to the 5th x sine squared x dx. See an odd power, peel that odd power. So in this case, let's again peel a cosine. Okay, seeing a cosine makes us think of cosine as the derivative, so sine must be the function. That suggests changing this cosine to the 4th into sines using the mother of all trig identities. So this term here is exactly cosine squared squared as 1 minus sine squared, quantity squared, of course, times sine squared, times cosine of x dx. Now the form of this integrand suggests substitution u equals sine of x. So there's a little bit of algebra to do here, expand our integrand and rewrite it as u squared minus 2u to the 4th plus u to the 6th du, which integrates quickly, and we'll substitute back in our sines here as u to obtain this general antiderivative. Okay, let's go ahead and talk about the half-angle formula. The half-angle formula is a strategy to use when we have all even powers of sine or cosine. So if there's any odd power of sine or cosine, peel. If there are all even powers of sine or cosine, we have to use the half-angle formula. These are the two half-angle formulas. So let's go ahead and evaluate the integral cosine squared. We don't have an odd power to peel, so half angle, expressing cosine squared as 1/2 plus 1/2 cosine of 2x dx. Now this first term has a quick antiderivative, and the second term does too, as long as you can make the substitution for the factor of 2x in the argument of the cosine. So here's that antiderivative, 1/2 x plus 1/4 sine of 2x plus an arbitrary constant. Other all even powers of cosine and sine work similarly. Here's another example. Let's go ahead and have a look at the indefinite integral of cosine to the 4th x. So we can see that cosine to the 4th can be expressed as cosine squared squared. So here is cosine squared squared. Expand, expand, expand. Rewrite this as 1/4 plus 1/2 cosine 2x plus 1/4 cosine squared 2x. Now here again is another all even power of cosine that we'll have to use another half angle identity on. Here's that other half angle identity. We've rewritten this cosine squared of 2x as 1/2 plus 1/2 cosine of 4x. Expand, 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 simplify terms, and we're left with the integral of 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x. Each of those integrates quickly, factoring in the argument of the first cosine 2x, the argument of the second cosine 4x, and we see that the general antiderivative has form 3/8 plus 1/4 sine 2x plus 1/32 sine 4x plus an arbitrary constant. Okay, let's go ahead and talk about secants and tangents, and we'll just sort of go through all of these secant and tangent integrals individually. Here's the first one. In general, we can try to peel a derivative. Oftentimes that doesn't work though, so we'll have to use a different route. Let's have a look at the integral of tangent x dx. So remember that tangent can be expressed as sine over cosine, and once we've written it as sine over cosine, there's a function and its derivative here, u equals cosine x, du equals sine x dx. Here's the substitution with a minus sign from that derivative of the cosine function, giving us the natural log of the absolute value of u. Of course, here that substitution was u equals cosine of x. Of course, we can go back to x world as minus the natural log of the absolute value of cosine x dx plus an arbitrary constant. Now, it's not unusual to express this in terms of secants also. And either of those forms will work, of course, just using the hop it up trick for natural logs here to rewrite that as the natural log of the absolute value of secant x plus c. Okay, let's have a look at the indefinite integral of secant x. A quick warning, this integral turns out to be annoying. Here's the strategy. Multiply numerator and denominator by the quantity secant x plus tangent x. When we do that and expand, what we see is that we get secant squared in the numerator and secant tangent in the numerator. And of course, there's a tangent in the denominator and a secant in the denominator. So this suggests a substitution, and that substitution, of course, is u equals secant x plus tangent x. So with this sort of sneaky substitution, the numerator is exactly the derivative of the denominator, and we can express the indefinite integral here in u world as the integral of 1 over u du. And of course, we can rewrite that as the natural log of u, which is just the natural log of the absolute value of secant x plus tangent x. Now, I mentioned that this is an annoying integral. It turns out that remembering the trick isn't a whole lot different than remembering the indefinite integral itself. So what ends up happening in this example is most often you just end up remembering the indefinite integral. Okay, let's do another one. How about the indefinite integral of secant squared? Well, as annoying as the indefinite integral of secant is, secant squared is a function that comes from a derivative we know. Of course, that function is just a tangent function. The derivative of tangent is secant squared, so the indefinite integral of secant squared is tangent. Okay, let's do another one. Let's have a look at indefinite integral of tangent squared. Well, we don't know any derivatives who give us tangent squared, but we do know a quick identity that relates tangent squared to secant squared. So of course that's the cousin of the mother of all trig identities. Tangent squared is secant squared minus 1. Now of course here we have two functions whose antiderivatives we know. So secant squared is the derivative of tangent, and of course 1 is the derivative of x, giving us the general antiderivative here of tangent x minus x plus an arbitrary constant. Okay, let's do another one. Here's another one, tangent cubed of x. So our strategy here is a little bit different. We can express tangent as tangent times tangent squared, express tangent cubed as tangent times tangent squared, and then we can turn this tangent squared into secant squared minus 1 with, again, our identity. Now, of course, there are two different integrals here. One of them is the integral of tangent times secant squared, and the other one is the integral of just tangent. So here, one should see a function and its derivative, and here we should see an indefinite integral that we just solved. So on this one, we'll try the substitution u equals tangent x. And on this one, we know that we can rewrite and use the substitution u equals cosine x. Okay, so doing that, we see that we get the following. The first integrates as 1/2 tangent squared of x, and the second one integrates as a minus, so positive natural log of the cosine of the absolute value of x. Okay, let's do another one. Here's another one, indefinite integral of secant cubed. This is a fun one that takes a little bit of work. We'll start off by writing secant cubed as secant times secant squared. Now, here's a function that we know how to differentiate, and here's a function that we know how to integrate. So that sort of suggests trying integration by parts. So here's our integration by parts substitution. U equals secant x, dv equals secant squared x dx. We can express our integral as u times v minus the integral of v du. So when we do that, we see that we end up with secant x tangent x, this is u times v, and then secant times tangent squared is the integral of v du. Now, tangent squared is something we've dealt with before, so we're going to rewrite that term as secant squared minus 1. So here is rewriting tangent squared as secant squared minus 1. And once we multiply that out, we see something familiar happens from our integration by parts experience. We see that we've actually reproduced the original integral. So writing that single integral as two different integrals, we see that one of them is the integral of secant cubed, and the other one is the integral of secant. We can take that first integral, move it to the other side, and write two integrals of secant cubed has to be equal to secant x tangent x plus the natural log of the absolute value of secant x plus tangent x. Of course, that's the integral of secant that we found earlier. Once we do that, it's as quick as dividing through by a factor of 2. We see that the integral can be expressed here as 1/2 times that entire quantity. So here is that integral of secant cubed in all of its glory, 1/2 times the quantity secant x tangent x plus the natural log of secant x plus tangent x. Again, kind of a cool application of integration by parts and the cousin of the mother of all trig identities, that is tangent squared is secant squared minus 1. And here's another example. Let's have a look at the integral of secant to the fourth. Here we can actually peel a derivative. So let's peel the derivative of secant squared is going to be the derivative. Of course, thinking of secant squared as a derivative, we're thinking of tangent as the function, suggesting that we need to get tangents wherever we can, and we can get tangents in for our secant squareds by writing tangent as 1 plus secant squared, or secant squared, excuse me, is 1 plus tangent squared. So here's that substitution. Secant squared is 1 plus tangent squared. The u substitution now is straightforward. We'll try u equals tangent of x. Writing u as tangent of x, of course, du is secant squared x dx. We're left with u squared here, integrates as 1/3 u cubed, and 1, of course, integrates as just u. Back into x world, we see that we're left with tangent x plus 1/3 tangent cubed x plus an arbitrary constant as our general antiderivative. Okay, folks, that's about it for integrals of secants and tangents. Hope you've enjoyed this video. We'll see you next time. Bye-bye.